Hello, I'm Yiluo. I will present our work exploring the role of centralization in IPFS. So before we start, have anyone heard about IPFS? Okay, a few. So let's begin with what is IPFS. So IPFS is a decentralized storage and delivery network which builds on peer-to-peer networking and content-based addressing. So to put it even simpler, it is a network where people can publish something and others can retrieve it. So what is IPFS in stats? So IPFS has been operational since 2015, and 31,000 nodes participate in the public DHT, and with 230,000 unique DHT clients per week. And we receive 120 requests per day, million requests per day. So how does IPFS work? So how to publish a file? So the first step is we import the content provider local IPFS and allocate a seed. So where seed is a hash and is also the identifier of the file. Then we do a DHT work to find the 20 closest peers to the CID. So, yeah. And then we store the provider record with these 20 closest peers. So now, how to retrieve the file? The first step is the requester do a DHT work to find the provider record storing peer. And then the requester connect to the provider and fetch the content. So as a fully decentralized system, IPFS faces some challenges. So the first challenge pertains to massive content publication. Here is a figure showing the content publication time in IPFS from different regions. We can see that at the median, it can take up to 8 seconds to publish a content. And at the 90th percentile, it can take up to 20 seconds. So this is acceptable for most of the common users who do not need to share many files. However, it is difficult for large content providers with billions of files to join the network and make them available in IPFS. The second challenge is content retrieval performance. So here's a figure showing the lookup latency in IPFS from different regions. So we see that at the median, it can take up to 1 second. And at the 90th percentile, it can take up to 1.5 seconds. So again, this is fine for many applications, but may not be good enough for latency-sensitive applications, for example, video streaming. So the third challenge is adoption. So in terms of mobile users and web users. So currently, to run a full IPFS node requires a computer. Well, we can see that 92.3% of internet users using a mobile phone of some kind. We want to make it easier for mobile and web users to use IPFS. So, therefore, to address these challenges, we designed and deployed 3 centralized components: IPNI, Hydra Boosters, and HTTP gateway. So the first component is IPNI, aka the indexer. So we designed and wanted to support massive content publication. We wanted to complement the DHT so that large content providers will publish the content to the indexer, and most of the normal users still use the DHT. And we make it as a high-performance key value store. So here is how the indexer works. So first, the content provider publishes an announcement message and telling the indexer that I have new provider records, please connect to me and sync. And then indexer sync the provider record with the content provider. So this step is specifically optimized to efficiently handle large amount of records. And unlike DHT, with a 24-hour TTL, there's no TTL in the indexer. So this involves trade-offs. So with the TTL, we minimize the communication overhead to delete a record, while without the TTL, we minimize the communication overhead to ping a record. So we expect that most of the large content providers will make their content alive for a long time, so the index does not have TTL for provider records. So okay, now the provider record is in the indexer. To retrieve it, the retrieval client can query the indexer using the seed and get the provider record. So finally, the retrieval client can get the data from content providers according to the provider record. So this is how indexer works. While the indexer complements the DHT, we still need optimization in the DHT. So to improve the DHT, we introduce the next component, which is Hydra Boosters. So Hydra Boosters is a new type of DHT node designed to accelerate content routing. So it contains first thousands of virtual Hydra heads, which is DHT nodes, and second, a shared database that stores all provider records. So we have developed an algorithm to strategically, uniformly place the Hydra heads in the Cadmia XOR space so that we expect that every peer is connected to at least one Hydra head directly. And the shared database allows every Hydra head to serve any provider record. So here is how Hydra Booster works. So recall, in step 2, we do a DHT work to find the closest peers to the CIT when publish the content. So in this step, we will hit a Hydra head because we are directly connected to one Hydra head. So then the Hydra head will store the provider record in the database. Then when we are retrieving the content, the provider record is already in the shared Hydra database. So when we do a DHT work to find the provider record, then we will hit a Hydra Booster head directly, immediately. And this Hydra head will serve the provider record immediately. So this will significantly accelerate content routing in DHT. So now we have the indexer complements the DHT and Hydra Boosters that improve the DHT. To actually broaden the adoption of IPFS, we need to make IPFS accessible for mobile users and web users. So thus we deploy the HTTP gateway. So it is, works as a HTTP bridge into the IPFS network. So to put it simple, it is a HTTP server with an IPFS node behind it so that users can access IPFS through the normal HTTP code. And additionally, the gateway enables cache of frequently retrieved content. If the request to the gateway hit the cache, the content will be provided immediately and without a need to entering the IPFS network. Now we have designed, implemented, and deployed these components. We then want to evaluate whether they do successfully address the challenges. So recall the first challenge is massive content publication. Our evaluation goal is whether we successfully support large content providers. So here we can see that there are around 600 providers in the indexer, while the indexer stores 100 times more provider records than the DHT. And the top providers in the indexer offer 100 to 1,000 times more provider records. So overall, we are happy with the result, with the indexer successfully handle the large content providers, and the normal users keep using the DHT. And however, there are certainly some trade-offs. The indexer is clearly a single point of failure. So failure could make significant volume of provider record inaccessible. So now we have 7 indexers operated by different stakeholders to federate the data, but it is still a challenge. Then we evaluate the improvement on content retrieval performance. So the evaluation goal is faster lookup time. We first see the lookup time of the indexer. We see that performance of indexer, either cached or uncached, is significantly better than the DHT. Then is how Hydra Booster improves the DHT performance. Here is a figure showing the lookup time with and without the DHT, without the Hydra Boosters. So we see a clear improvement. As of the median, the improvement is 3.7% or to 36.5%. However, one problem is the high operational cost of Hydra Boosters. So we need to spend thousands of dollars per month on it to keep it running. Then is the retrieval performance from the gateway. Recall the gateway can cache frequently accessed content and thus improve the retrieval performance. Here we see the cache hit rate is around 80%. And for cached content, the lookup time can be 100 times faster than to get it from the DHT. We finally evaluate the improvement of adoption brought by the gateway. We see that 32% of the total traffic, 90% of the total requests, and 44% of the total users are from mobile. And 51.6% of the total traffic and 29.8% of the total requests come from a referral website. So this confirms the improvement of adoption from mobile and web users. While it comes with a trade-off that it sacrifices the end-to-end verification. So the seed is not matched against the content served, so which may potentially lead to a man-in-the-middle attack. So in conclusion, overall, our findings highlight the persistent challenges that exist in deploying an operational decentralized system with tight performance constraints. Equally, we have highlighted the challenges of overcoming traditional issues with centralized deployment. So for example, single point of failure. Thus, we emphasize that developers must make judgment calls about how to balance such trade-offs. And in terms of IPFS, we will continue working on the research and development of decentralized protocols. And we hope that IPFS can eventually perform similarly even without these centralized parts. So thank you.